Okay, we're going to verify a trigonometric identity here. It says cosine squared x, and in parentheses 1 plus tangent squared x, close parentheses, equals 1. In order to complete this, we're going to make use of a quotient identity and a Pythagorean identity. The quotient identity states that the tangent of theta equals sine of theta over cosine of theta. The Pythagorean identity states that sine squared theta plus cosine squared theta equals 1. Our first step is going to be to distribute the cosine squared x term that is on the outside of the parentheses. So cosine squared x times 1 gets us cosine squared x, plus cosine squared x times tangent squared x gets us cosine squared x tangent squared x equals 1. Okay, now our next step is going to be to rewrite all terms as either sine or cosine. If something is already sine or cosine, it just stays the same. So cosine squared x will stay the same. Cosine squared x plus this cosine squared x will also stay the same. What we are going to do is change the tangent squared x, and we've said tangent is equal to sine over cosine. If tangent is sine over cosine, then tangent squared is sine squared x over cosine squared x. And that still equals 1 on the right side. Now, this cosine squared here on the outside of the parentheses, we can rewrite it as a fraction, and we can rewrite any number, whole number, as a fraction by putting it over 1. If you notice, there's a cosine squared in the numerator and a cosine squared in the denominator. Therefore, they cancel each other out, divide out, and become 1. And what we're left with is cosine squared x plus sine squared x equals 1. Now, because this is a Pythagorean identity that we have stated here, we are finished with the problem, and we verified that this is indeed an identity. Cosine squared x times 1 plus tangent squared x is equal to 1. Okay, next up, we have verified that the equation is an identity. Now, this one is a little bit more involved than the previous one. It says secant of 2x equals, in parentheses, 1 plus sine x times 1 minus sine x plus 1 minus cosine x times 1 plus cosine x. All of this over cosine squared x minus sine squared x. It's important to note that what we're trying to do is break down the more complicated side so that it winds up looking like the simpler side. And the simpler side in this case is definitely the secant of 2x. Now, this is a double angle because we see that there's a 2 in front of the x. There is no double angle identity for secant. Since there is no double identity for secant, our first step will have to be to rewrite secant as its reciprocal, 1 over cosine. So I'm going to write here 1 over the cosine of 2x equals, and we still have 1 plus sine x times 1 minus sine x plus 1 minus cosine x times 1 plus cosine x over cosine squared x minus sine squared x. Now we're going to make use of the difference of two squares. The difference of two squares states that if you have a term squared plus another term squared, it can be factored into, as long as they're perfect squares, into the square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term. And this works in reverse also. So I'm going to rewrite 1 over the cosine of 2x equals, we're going to use this difference of two squares property in order to multiply what's on top. We have 1 plus sine x times 1 minus sine x, and when we multiply that, we're going to get 1 squared minus sine squared x plus 1 minus cosine times 1 plus cosine is going to give us 1 squared minus cosine squared x. And once again, our denominator is going to remain the same. Now, 1 squared is just 1, so we're going to erase the little exponents right there. And now, in the numerator, we're going to combine like terms. So we have 1 over the cosine of 2x still here on the left, and our denominator on the right remains the same, cosine squared x minus sine, little technical difficulties here, minus sine squared x. Now on top, the 1 and the 1 will come together to make 2. And then we have minus sine squared x minus cosine squared x. Next up, this takes a little bit of ingenuity here. So 1 over the cosine of 2x, that still remains the same. And on the bottom, we still have cosine squared x minus sine squared x. Now the top, there's a little trick we're going to do. The 2 remains the same. Notice that we have a sine squared and a cosine squared, but their signs are negative. Now, we know here we have a Pythagorean identity that states the sine squared plus cosine squared equals 1. In order to make these two into a positive, what I have to do is factor out a -1 from both terms. So we're going to take -1 out of both terms. If I take -1 out of negative sine squared, it becomes positive sine squared. If I take -1 out of negative cosine squared, it also here becomes positive, and we have cosine squared x. Okay, next up, once again, we rewrite 1 over the cosine of 2x, and we rewrite the denominator once again, so cosine squared x minus sine squared x. We rewrite the 2 and the -1. Remember that sine squared plus cosine squared equals 1, so inside these parentheses, we're going to replace that with a 1. Now, let's continue the top. 2 minus 1 is just 1. And on the right, we have cosine squared x minus sine squared x. On the left, we have 1 over the cosine of 2x. Now, you stop one of these problems when you have the left side equal to the right side. The numerators are the same. The 1 and 1 are the same. On the bottom, we have the cosine of 2x equals cosine squared x minus sine squared x. So this is actually done because from the double angle formula, we know that the cosine of double an angle is the cosine squared minus sine squared, which is exactly what we have in the denominators. Therefore, we have verified the equation and completed.